Hello everyone. This is Rashid Kibria from Fixed Research, University of Florida. Today I will talk about my developed EQUICF tool. The main purpose of this tool is to verify the control flow equivalence of the FSMs extracted from the RTL design and also from the gate level netlist abstraction. We write control FSMs using RTL codes that can be either in Verilog, system Verilog, or whatever. But that is a very high level specification of a certain control FSM. And after logic synthesis, you get a gate level netlist of that FSM. So what is the equivalence between the FSM, which is present in the RTL description, and the FSM that can be extracted from the gate level netlist? We need to verify that. That's why EQUICF tool stands for EQUI. This part stands for the equivalence, and CF stands for the control flow. So this tool is fueled by my tool RTL FSMX, and also the report generated by FSMX Ultra tool will also be used because it basically provides us the information about the control FSM extracted from gate level netlist. So I will now try to run the tool. The first task, you have to use some sort of environment setting in our ECLinux server. Here, you have to use the source apps settings command. And after that, this cds.lib file will be created, but we do not, of course, require it. So, and then I will change the permission for the user interface, and finally, I will invoke the user interface. So if I write /UI, it will open up a graphical user interface for you. And then you can load all the files here as you require. The first task, you have to read all the RTL dependency files. These files include the macro files. That means the external defined statement holding files or parameter storing files, or any external files on which the RTL design is dependent on. These we call, these are normally known as macro files. So I will, in this demo, I will analyze the OPENMSP430 from opencourse.org and try to see whether the FSM extracted from the RTL description is equivalent to the FSM extracted from the gate level netlist. That means we need to check whether the RTL STG is a subset of the gate level STG. The EQUICF tool basically performs this structural analysis to provide you the equivalence report. So I will now first load the designs. So the dependency file, and then I will load all the RTL Verilog files. We have to add two more inputs. These two inputs come from FSMX Ultra report. That is basically the gate level STG information. The first one is the statistics file, which contains all the register information. The second one is the extracted gate level STGs by FSMX Ultra, and all of these STG files are in text format, so they are human readable. After selecting this, you will hit open, it will add this. The last task, I will add the tool here, and you can find the tool inside this tool directory, and this is the tool. Then I click on the verify control flow equivalence button. It will start running the tool automatically. Now it is very fast. So it will finish it. Yeah, you see, the analysis has been finished within just a few seconds. After execution, we can hit on the exit button and it will close the graphical user interface. So in this file or in this destination, we'll see 4 state transition graphs. All of these are basically the gate level STGs in .png format. There is another text report generated by my tool automatically. It shows you the FSM control flow equivalence report. Just to have a quick overthrow, uh, just have a quick look here at this file to get idea for what it tells about, what are the features here, and this sort of stuff, so that we can correlate the associated gate level STGs with that. In this report, if you look here in this part, the FSM control flow equivalence report is shown. So it first shows you where your FSM is located. That means the RTL design file which contains the control FSMs. It needs to be noted that a certain design can have a single FSM or more than one FSM. That's why my tool also provides you the FSM identifier so that you can correlate with the associated gate level STG. Because if you look here, you will see that this OMSP underscore front end, this is the design module name, and it has 1 and 2 because there are 2 control FSMs present in this design module, which were extracted by my tool. So that's why this ID is important because it tells you, which gate level STG you can correlate according to that. If you have a single control FSM, then you will just have a single FSM ID that is simply 1. But if you have multiple FSMs, then it will be 1, 2, 3 consequently. So this OMSP underscore DVG module actually holds a FSM, which is a state register that is described in the RTL description as mam underscore state. After logic synthesis, you get the register, and that register is this one. And my tool is also showing you the state register size there. Finally, it also tells you the transition count, which is present in the state transition graph extracted from the RTL abstraction. That is 7 here. And it is also showing all the 7 state transitions that is present in the RTL STG. But if you look here, the total number of transitions in the extracted gate level STG by FSMS Ultra is also 7. So all these 7 state transitions, they are also present in the same gate level STG. That's why we do not have any hidden transition that can be found in the gate level state transition graph. Now, if we look for another example, for example, the Open OMSP underscore front-end module, here I have mentioned there are 2 control FSMs. So there are 2 FSM IDs here, 1 and 2. Now, for the first control FSM, the state register was described using I underscore state. And here we see the register name that is found in the netlist abstraction. So the size of the state register is 3. There are total 12 state transitions in the RTL STG, and all of the state transitions are shown here. We have total 15 state transitions in gate level STG. So in these 15 state transitions, 12 state transitions which are present in the RTL, they are also present, but we have some more additional or hidden state transitions here. And the total count of gate level is these hidden transitions in gate level STG is 3, and that is also shown here. And here is a much more complex FSM, which has total state register size of 4. There are total 52 transitions in the RTL STG. All of them are shown here. And there are total 55 state transitions in the gate level STG with 3 additional hidden these transitions in the extracted gate level STG. Finally, my tool also provides you the peak memory usage and also the overall runtime. So if you look here, this tool is very requires so much low memory, and also it is very fast because this OMSP 430, this design is a massive design. It has total 31,000, over 31,000 lines of RTL code, and has total 11,000 ASIC equivalent gate in the netlist. And obviously, this the last control FSM, which is controlled by E underscore state, is the most complex one because it has lots of transitions and lots of states here. I mean, there are total 16 states and also a large number of state transitions. So if we now look here at the graphical part, so if I open up one STG, so this STG, the gate level STG is present in the OMSP underscore DBG underscore UART module. There is only one control same. That's why you get here a single underscore one. And if I hit open, it will show you the annotated gate level STG. So here the black transitions, these are the state transitions which are present in the RTL abstraction and also in the gate level abstraction. But the red ones, they are only present in the gate level STG, which was extracted by FSMX Ultra. So if you look here, it clearly shows you that RTL STG is a subset of gate level STG. That's what I have already mentioned in my papers. That is logical, right? Because after logic synthesis, you are getting the same FSM but with more transitions. That means the RTL STG will also be present there, and also you have some additional hidden state transitions that can be found by my FSMX Ultra tool. So this was a quick overview of my EQUICF tool. I will make more videos on it, and so stay tuned. Thanks for hearing.